Hello there, and welcome to today's problem. Today we'll be looking at making change tree, a problem that was requested by binary search user Tiago Leobuns. So let's get started. So, given a list of integer denominations and an integer amount, return the number of combinations there are that sum to amount. Mod the result by 10 to the 9 plus 7. So this is a really popular problem that is presented to demonstrate patterns in dynamic programming. But I think one important step that we need to look at first is how do we brute force this solution? And I will show you that right now. So, one idea we could have is starting from our initial amount, which in this given example is 6, we could try applying each coin. So, if we had coin 1, 2, and 3, we could try doing a recursive call with the amount minus the first coin, the amount minus the second coin, and the amount minus the third coin. So then we would reach the subproblem with 5, 4, and 3, and we would just have to sum the result from each subproblem. But this approach doesn't work, and here's why. Like here I highlighted two paths, the path that does 6, 5, 3 and the path that does 6, 4, 3 like this. So in the first path, first we pick the first coin and then the second coin, and in the second path we pick the second coin and the first coin then. So you can see that we reach the same subproblem, but the order of the coins is different, but they would be counted separately. But in this problem we don't want to count different orders because they represent the same coins. So we need to find a way to just count every permutation once. So here's how we do this. So this may seem intimidating at first, but it's really simple. Let me show you why. So at first, we consider the first coin in our given list. So this would be the coin number 1. So here it is represented by the root of the tree here. And then we iterate over every possible number of that coin in our answer. So potentially our answer could have 0 times that coin, once, 2 times, 3 times, etc. until it is impossible to use that coin in our answer. So basically you would iterate over every multiple of that coin that fits in our given amount denoted by k here. So here I highlighted all the partial answer. So the first node here on the left is the one where we use the first coin 0 times, then we use it once, twice, 3 times, and etc. And then we go over to the next coin. So we don't ever consider the first coin ever again. We just try to solve the subproblem using the following coin. So then we would reach the second coin and we would apply the same procedure. Check all the multiples that fit in the given k and sum all the subproblems from there. And each time we reach a subproblem where the k is 0, so the amount is 0, it means we have exhausted all the possible amount we had available. So in that case we found a valid solution, so we can return 1 because it counts as one solution. So this would work, but it's not quite optimal, even considering brute force, because we have to do a loop for all the multiples. So we can simplify this. So instead of checking every multiple, we can consider the first coin once again, like the same strategy as the previous method. But now we have only 2 children to our current problem. So either we add the current coin to our current solution. So here we would add the 1 coin, and then we would reach the subproblem where k is equal to 5, but we're still considering the first coin because we can remove the first coin once again. And can repeat that as long as the coin fits in our problem. But when we want to consider the cases where we don't use the current coin, we can just go to the right here. So here we do I plus equals 1. So it means we stop considering the 1 coin. So here, when we go to the right, it means we ignore the first coin completely. Here it means we use the first coin once, and then when we go to the right, it means we ignore the rest of the 1 coins we could add. But as long as we're going to the left like this, we keep adding the coin as long as it's possible. So let's demonstrate what the solution would look like. So let's say we use a brute force function here, and each node here represents a recursive call we're doing. So we would have I and k. So I is the current coin we're considering, and k is the remaining amount. So if we ever reach k is equal to 0, we found the solution. If k is less than 0, so it's negative, it means we use the coin that we couldn't use, so then we return 0. If we reach the end of the coin array, the denominations, it means we don't have any coins left, and if there's still some amount remaining, it means there's no valid solution. So now we want to explore both children. So the first case here is when we use the current coin. So how do we do that? Well, let's say we have our answer here. So we can check if the current denominations fit in the amount. So it's smaller or equal than the amount. Then we can add it. So it would be our answers added to dp of I. So we keep considering the current coin. And from the amount, we remove the value of that current coin. So it would be denominations I like this. And since we're checking if the denomination is smaller or equal than amount, we can remove this check here. And then the other case is where we skip. So we just skip the current coin, and the k is left unchanged since we haven't used the current coin. And I meant to write answer here, and then we can return our answer like this. So we start from the start of the array, and at the start we have amount as k. So this will work. I'm just gonna add, we don't have to add it. dp is not defined. I called it brute force. This is denominations. I'm reading the wrong one. All right. Segmentation fault. Oh, come. Fuck. Oh, I checked amount here. I meant to check k. Okay. Yeah, so here we have it. We have implemented exactly this. So removing the current coin or passing on to the next coin, and it works. But if we check for greater test cases, obviously it will exceed the time limit, and the reason for that is we have a lot of overlapping subproblems that we keep checking on. And you see, for every node in this tree we have 2 children, so if our tree has a depth of n being the number of coins, it means we have an exponential problem on our hands, because it will be 2 to the n, and that's ignoring the amount that defines the depth as well. So since we have overlapping subproblems that is represented well by this, if we like use a 1 and a 2 or another coin where they have like the same k at the end, well, we will recompute the same thing for no reason. We already have the answer to that subproblem. So if we want to do dynamic programming, we can just memorize. So that would be for the top-down approach. Basically, when we do top-down programming, you just have to come up with the brute force and then memorize your function. So this will work. It will reduce our complexity greatly. So the complexity would be the number of coins, we could call it n, times k. But I forgot to add the mod. So now this is considered dynamic programming, so we could rename brute force to dp. So you see that it still times out. And the reason for this is, even though our complexity now is n times k, because the constraints on this problem are so tight, because of all the recursive calls and the hashing, we actually exceed the time limit. So to solve this problem, we have to convert our top-down dp to bottom-up dp. So using a dp table and starting from the base case and going up from there. So I already coded a solution here and we can go through it. So let's look at this. So now, instead of hashing all the individual states, the state being the parameters that were passed to our brute force function, now we're gonna use a 2D table to store all those subproblems. So we start with a matrix of width amount plus 1 and height equal to n, n being the number of coins we have. And the leftmost value will be equal to 1. It means each time we reach the k equals to 0, it means we have one valid solution. And now we apply the same principle as our top-down solution. So for every index in our matrix, we add the top value, so dp I minus 1k. So this is the case where we skip the current coin. So right here, we skip the current coin. And otherwise, we use the current coin. So here we remove the denomination. So we're looking up earlier on the table in the same row, the number of possible solutions there were from there, and we add it. So I can print what it looks like if you want to visualize it better. Okay, so here we have 2 coins and 6, so the height of our table will be 2, and here we will have 7, because we have to consider the 0 as well. So we have 0, 1, 2, 3, 4, 5, 6, so that makes 7 indices. So when k equals to 0, we have one possible solution, whichever coin we're considering. But then we go to the right. So here it's when k equals to 1 and we're considering the first coin, k equals 2, 3, 4, 5, 6. And then we check at the last index here, which is when k equals to 6 and we're considering all the coins. So that's our final answer here. And if we submit this, it's gonna work, but you see that my submission is only faster than 26% of other Python submissions. That's because there's a simpler way of doing this using one-dimensional DP. So how do we convert from 2D DP from 1D DP? Well, it really depends on the problem, but I just want to point out that when we decide to skip the coin here, we're just doing dp of I k equals to dp of I minus 1 k. So when we do that, basically for each row, we're just copying the previous row down the current one, and then we're adding the cases where we add the current coin. So instead of copying the row each time, since there's only a dependency on I minus 1, we can discard all the previous rows and just reuse the last row. So here I have an example using one-dimensional DP. So I can put them side by side so we can compare them. So here we only have one dimension in our DP. We don't use the height based on our number of denominations. And the first index equals to 1. So here we remove this for loop completely. We remove the creation of the table in our memory, so it really speeds things up. And then we iterate over every denomination. And then we check if it fits in our current position, then we add it. So we're getting rid of this step basically. This loop is unchanged, we just remove this because it's just copying the previous row. So we just keep iterating over the same row, and instead of copying, we just apply this if statement here. I'm just gonna print it like this, so you can see the similarity. So in the first case, we keep every single row, but in the second case, we just keep the last row that was used and just apply changes on it. And it gives us the same answer. We just take the last index, and it's our problem we're trying to solve. So this is the final answer. And if we submit this, you're gonna see that we have a much faster solution, because processors do a lot of optimization with caching and everything. So when you reuse the same memory, there's hopes that it's cached. So it's hard to demonstrate exactly the benefits, but there's memory locality used. So, and all this memory allocation that is removed and all the iteration, it's just better overall. So there you have it. If you have any questions, don't hesitate to ask them in the comments. And if you have any suggestions for following problems, please let me know. Thank you for watching. See you next time.